Okay, YouTube, in this video we're going to prepare to graph functions that are exponential. And we're going to start with a couple of very straightforward functions, but this one that we're going to start with here, you notice it says y equals 2 to the power of x. Now the fascinating thing here is that with exponential functions, our base is some positive constant that's not equal to 1, and our variable is up in the exponent. So the question really becomes, can I take 2 to the power of 2? Well, of course. 2 to the power of 3, of course. 2 to the power of 4, of course. Can I take 2 to the power of something like 1.73, 205 or something like that? And the answer here is really, truly yes. Before we prepare to graph these, what I want to do is basically mention something here. We say we're familiar with expressions involving b to the x, where x is a rational number. That is, I can take b to the m over n, because recall that this really means the same thing as we're taking the nth root of b to the mth power. And so the reason why I mention this is because it means that if I were to say take b to the 1.7, you guys, that's the same thing as b to the 17 divided by 10. And writing b to the 17 over 10, we know that's the same thing as b to the 17th power but the 10th root of that, and I could certainly find that. And let's say now 1.7, what if I wanted to do b to the 1.73? The same method applies here. We could say b to the 1.73 is really b to the 173 divided by 100, which is this b to the 173rd power, 100th root of that. Basically, what I want to note here is that the definition of y equals b to the x includes all numbers for the domain of x, okay? And the reason why is because where all of these x values that we're plugging in, we can usually write them as some rational value right here and evaluate this and get some value for that, b to the power of that thing. So here's what I want to wonder here. So you may wonder what b to the x means when x is an irrational number. What if I can't write it as a ratio like this, such as b to the square root of 3 or b to the pi here? One thing I want to show you is this. B to the 3 here, or b to the square root of 3. The square root of 3 is, let me find this here. 3, we want the square root. The square root of 3 is about 1.73205, and so you'll see this decimal right here. But what if I did want to take b to the square root of 3 power? We say using closer and closer approximations for the square root of 3, that is, the square root of 3 is about this right here. We can think of b to the square root of 3 as a value that has successively closer approximations of this here. So just like I did, b to the 1.7 is about b to the 17 over 10 power, and we could find that root. And I could find b to the 173 over 1,000. This would be b to the 1732 over 1,000. This would be b to the 173205 over the, it looks like 100,000 here. But basically, we can get closer and closer approximations. So what this means is that when we talk about the graphs of exponential functions, we're going to be able to plug in all x values. And so the domain is always going to be all real numbers. So what we're going to do is we're going to graph this function y equals 2 to the x. And so really quickly, what I want to do is I want to start by finding the x and y intercepts. Now to find an x-intercept, let's go ahead and admit to find an x-intercept, what we need to do is we need to plug in 0 for y. So using this function right here, I'm going to say 0 equals 2 to the power of x. And the first thing that I want to write here is that it has no x-intercepts. The reason why is because there does not exist a power that we could take 2 to the power of and get 0 for an answer. So this graph will have no x-intercepts. In terms of y-intercepts, we'll plug in 0 for x. So plugging in 0 for x, we get y equals 2 to the 0 power, and anything to the 0 power, of course, we observe as being 1. So I'm going to go ahead and put our y-intercept on my graph here at 0, 1. And then we're going to make a table of values. Now this table of values, what I'm going to do is I'm going to use a nice little battery of values here, x, f of x, and we're going to do -3, -2, -1, 0, 1, 2, and 3. So now plugging these in, what we're really doing is we're taking 2 to the power of these inputs. So for instance, 2 to the power of 0, we just observed here, is 1. And I'm going to put a big box around this, and I'm going to label this as our y-intercept. But also what I want to point out here is if we take 2 to the positive 1, we get 2. 2 to the 2, we would get 4. 2 to the 3rd power, we would get 8. And so what you're noticing here is that every time x is increasing by 1, this is doubling. And so by the same reasoning, if I were to go backwards here, if my x's were to decrease by 1, I would be taking these and cutting it in half each time to get to the previous y value. So if I said 2 to the -1, let's go ahead and write this here, 2 to the -1, what I really mean is the same thing as 1/2. And if I did 2 to the -2 power, I really get 1 over 4. And if I do 2 to the -3, I really get 1 over 8. And really all I've done was I took all these values here and I split them in half to get the one previous to it. So one thing I want to notice here is this, in this video, we say 2 to the 2, you'll notice that 2 to the 2 came out to be 4. So 2 to the -2 actually comes out to be its reciprocal 1/4. 2 to the 3, that equals 8 if you look at our table here. 2 to the -3 equals 1 over 8. So what you need to notice is this, whenever you have a negative exponent, we can take this and interpret it as being over a 1 here, but when you move its base across the bar on this fraction, that is, I could write this as 1 over 2, but we'd say it'd be 2 to the positive 2, which comes out to be this 1 over positive 4. In other words, whenever you move the base of something over the bar on a fraction, its exponent changes its sign. So 2 to the negative 3, that's 1 over 2 to the positive 3, and that's still the same thing as our 1/8 here. But also know that 2 to the negative power is not a negative answer. It's just the reciprocal of what you would get if you did 2 to the positive of that power. Okay. So using this table right here, let's go ahead and graph our points. We say 1 would be at a height of 2, 2 would be at a height of 4, 4 would be at a height of 8. We can see that these are doubling every time. And as we go backwards, we say negative 1 is at a height of a half, negative 2 is at a height of a fourth, and negative 3 is at a height of an eighth. What we can observe here is this. If we were to keep getting more and more negative numbers, like 2 to the negative 4, if I said 2 to the negative 4, well, that's the reciprocal of 2 to the 4, that'd be a 16th. And 2 to the negative 5, that's the reciprocal of 2 to the 5th, so 1/32. You can see as if we were to keep going to the left here, our values are going to keep getting smaller and smaller, but there is never an exponent that I can take 2 to the power of to get exactly 0. We stated that here. So important things to know about your exponential graphs. One very important aspect of every exponential graph is that we have a horizontal asymptote that is on the x-axis or at y equals 0. We also say that this point 0, 1 was on our graph. So if we were to graph this now, what we get is this graph that if I were to describe this has a domain of all real numbers and a range of 0 to infinity. Okay, I would also write that this is always increasing, and I also want to observe that as we go from left to right, our slope is getting steeper and steeper and steeper and steeper on our graph here. Those are supposed to be lines tangent to my graph there. But essentially we see our exponential function graph here, 2 to the 0, goes through 0, 1, has an asymptote here, and then we could just plug in some extra values. So before we tune out this video, what I want to do is graph y equals 3 to the x. So really quickly, you notice that I left off the x-intercept here, and one reason why I want to say that is because this right here, we know that because it's an exponential function, has a horizontal asymptote on the x-axis, y equals 0. Okay, so plugging in some extra values here, let's start with our y-intercept. I would just put that on the table right here in the middle. When you plug in 0, we get 3 to the 0, which equals 1. So again, we get 0, 1 that shows up on this graph right here. 0, 1 would be right here. Now if I were to plug in 1, 2, and 3, I say 3 to the power of 1 is 3, 3 to the power of 2 is 9, 3 to the power of 3 is 27. So if I'm going backwards here, we say negative 1, negative 2, negative 3, I would have 1/27. This would be 1/9. This would be 1/3, be reciprocals of these. So graphing these this time, we say 1, 3, 2, 9, that's way up here, 3, 27, I can't even put on this graph. This one here though, if we go left, would be at a third at negative 1. When x is negative 2, we're at a 9th. Here we're at a 27th. You see that this graph here, when we draw it, is really close to the asymptote. And in terms of how it's growing, I would say it's growing even more quickly than this graph that we had here. So in terms of what these two graphs have in common, exponential growth, they have a horizontal asymptote on the y-axis, or on the x-axis, horizontal asymptote at y equals 0. There's our horizontal asymptote. Okay, and one other thing we want to write here is that it goes through the point 0, 1, and you could see that if we were to plug in 0 to any function that is exponential, we say y equals some positive base to the 0, we could always get 1. So it'll always, let me switch back to red, always pass through 0, 1. If it's exponential, it'll always do this. So in the next video, we'll look at some exponential decay. Cheers.